Okay, we're ready to do section 1.3 now. Now here we're graphing some functions. Now part of it is reading the graph. Some of the things that you do a lot in calculus are increasing, decreasing, constant. We mentioned that a little bit the other day. So increasing is when it has a positive slope. Decreasing is when it has a negative slope. Constant when it has a zero slope. So if it's going up, if it's curving upwards, it's increasing. If it's curving downwards, it's decreasing. If it's horizontal, it's constant. So like here on this first one, if I said, when is this function increasing? And when you list the intervals, you always use the x coordinates. So notice here, it's going up right over here, it's increasing. So that's on the left, that's negative infinity. It keeps increasing till we get to negative 3. So you could say it's increasing from negative infinity to negative 3. Where is it decreasing? Well, where is it sloping downward? We'll see here it's going down. So it's decreasing here. Looks like from negative 3, going to keep going here. Don't know where. It looks like maybe, if you look at this, doesn't it look like maybe negative 1 might be a vertical asymptote? So could we say it's decreasing from negative 3 to negative 1? And then here it's going down. It's decreasing again. This would be from negative 1 over to 4. Again, you always use the x coordinates for your boundaries. So it's decreasing from negative 3, keeps decreasing till it gets really close to negative 1. Then it's decreasing here from really close to negative 1. It keeps decreasing till we get to 4. Or this one. Where's it increasing? Well, it's going up here. It has positive slope here. That's from between, looks like between negative 5 and negative 4. So it's increasing there. Looks like it's increasing again over here. Well, that's from 3 over to 5. So from 3 to 5. And on these intervals for increasing and decreasing, you always put parentheses. Don't worry about brackets. Decreasing, well, it's decreasing here from negative 4 over to negative 2. Looks like it's decreasing again here from where x equals 1 over to where x equals 3. And it's constant. It's horizontal here, so it's constant. It looks like from negative 2 to positive 1. Okay. Now, along with that, we have mins and maxes. Now, you have relative minimum and relative maximum, and you have absolute min and absolute max. I actually had one calculus book once that called it global max instead of absolute max. So relative min is just a point that's higher than the points around it. What you look for is a relative min is going to be where a graph goes. If you think about it, the graph goes from where it's decreasing to where it's increasing, right? You see from decreasing to increasing, there's going to be a relative minimum down there. So we look at this graph, on this graph here, is there anywhere where it goes from decreasing from negative slope to positive slope? I don't see any on there, so there's no relative minimum. A relative maximum is the opposite. It goes from increasing to decreasing, gives you a high point. So here, notice we're increasing, and there we're decreasing. So we're going from a positive slope to a negative slope. So this is a relative maximum right there at negative 3. So it looks like we have a relative maximum at negative 3, 2. We'll list the point when it's a relative maximum. So at x equals negative 3, another way to look at that is at x equals negative 3, there's a maximum of 2. The x coordinate is where it's located. The y coordinate is the maximum value. Or this one, relative min. Again, we're looking for relative min from where it goes from decreasing to increasing, or negative to positive. Well, notice here we have a negative slope, so we're decreasing. Then we have a positive slope, so we're increasing. So we go from negative to positive. So that's a relative min there at 3, negative 4. So you could say it's at 3, negative 4, or you could say at x equals 3, it has a minimum value of negative 4. Relative max, well here we're going from positive to negative, so from increasing to decreasing. Well here we're positive, then we're negative. So this would be a relative maximum here. That looks like it's at negative 4, 1. So we could say at x equals negative 4, it has a maximum value of 1. Now these points here aren't either, because here it goes from negative to 0. So that's not 1. Or here it goes from 0 to negative, or constant to decreasing. So that is not a relative maximum. Okay? So that's that part. Now the next thing is here, graphing a piecewise function. You probably haven't seen a lot of piecewise functions, but they occur a lot in real life. A piecewise function, it's called that because it's in more than one piece. You usually see 2 pieces like this one, it could be 3. Now what happens is there's 2 different functions on this one, and they each have their own domain. So what this means is whenever you have any x values that are less than or equal to 1, you use this part of the function. When you have any x values that are greater than 1, you use this part. So if we wanted to graph that, we could plug in some numbers. So let's plug in some numbers here, like a number greater than 1, like 2. So if x is 2, 2 times 2 is 4, plus 1 is 5. So the point 2, 5. Or notice like here, it's equal to 1. Let's try 1. We plug in 1. 2 times 1 is 2, plus 1 is 3. 1, 3 is on there. Now, it's also helpful to look at each one and see what shape it's going to be. If you look at this one, isn't that going to be a line? Whenever x is to the first power, that's a line. So here, it starts at 1, so it's a line that goes here. So that's part of the function. Now, if we plot the other part, this is when x is, I'm sorry, I did that backwards. Doggone it. Start that over again. Sorry, I messed that completely up. I was thinking it said x is greater than or equal to 1. It's less than or equal. So we can still use 1, 1, 3. Use a number less than 1 like 0. 2 times 0 is 0, plus 1 is 1. So we have the point 1, 3. We have the point 0, 1. Again, this is a line. It only goes as far as x equals 1. So it's only going to go this far. So this is going to be a line that looks like that. Now the other part is when x is greater than 1, so that's over here. Notice this one, if it's squared, that's a quadratic, so that's a parabola, so we want to keep that in mind. Now even though it doesn't equal 1, let's plug in 1 anyway. If we plug in 1, 1 minus 1 is 0, squared is 0. So we get the point 1, 0. Now it doesn't include that point, so let's put an open circle there, right? So x equals 1 is not included, but it helps us for our graphing to put that there. Now let's try another point bigger, like let's try x is 2. 2 minus 1 is 1. 1 squared is 1. So the point 2, 1 is on there. Let's try one more. Let's try 3. 3 minus 1 is 2. 2 squared is 4. So 3, 1, 2, 3, 4. Now we said this looks like a parabola, so this is going to look like this. And that's our graph. So you plug in numbers for each domain. So here we plugged in numbers less than or equal to 1 into this one. We plugged in numbers greater than 1 into this one. And it's always good to plug in the number where they meet, like here at 1, to see what you get. Just remember, like here, we're going to put an open circle because that's a greater than, not greater than, or equal to. All right, the next thing is even and odd functions. Well, an even function is symmetric to the y-axis. So that means it's the same on both sides. So this is an example of an even function. If you flipped it over the y-axis, does it fall right back on top of itself? Yes. So symmetric is, even is symmetric to the y-axis. To check and see if it's even, you substitute negative x in for x, and then simplify it and see if it matches the original function. You might remember doing this in algebra. An odd function is symmetric to the origin. So for that, you substitute negative x for x, and you also do negative y for y to check and see if it's odd. It's harder to visualize an odd function. This is an odd function here. You can think about if you rotate it at 180 degrees and it lands on top of itself, or if you pick a point, if I go across the origin, is there a matching point on the other side? That's one of the things I look for. All right. So if I tell you I have a point -2, -9 that's on an even function, name another point. Well, -2, -9, that's going to be over here to the left. If it's even, if it's symmetric across the y-axis, shouldn't there be a matching point over here? So if this is -2, 9, this one would be +2, 9. So we said you could substitute negative x for x. So here, notice we just changed the sign on our x. Now, how about if -2, -9? Oh, I'm sorry, that said -9. I used -2 positive. I'm doing really well here. -9. So I'm sorry, that picture should have looked like this. So -2, -9 is down here somewhere. So if it's symmetric to the y-axis, it's going to have a matching point over here. So that would be +2, -9. Now, if it's on an odd function, it's symmetric across the origin. We're going to change both signs. Here, we just changed the sign on the x. Remember, if it's odd, we're going to put negative x for x and negative y for y. So we're going to change the signs on both of them. So change the -2 to a +2, change the -9 to a +9. Because if you think about that, like -2, -9, we said is down here somewhere. If it's symmetric across the origin, shouldn't there be a matching point up here? So +2, +9. Okay. Now to check and see if it's even, odd, or neither, we're going to do what we said up here. Like here, if we want to check and see if it's even. Well, the first thing I do is I change this g of x to a y. Now, if we want to see if it's even, we substitute negative x for x. So here we're going to put a negative x in here. So that's a negative x cubed minus a negative x. Now simplify that. Well, if I take a negative and cube it, it stays negative. And here minus a minus is a plus. Now look at that. Is that the same as what we started with? No, it's not. So this one's not even. Now let's check and see if it's odd. Well, now we're going to put in negative x for x, just like we did here. So this part's going to be the same as we just did. Only now we're also putting negative y for y. So here where there's a y, we're going to put a negative y. So we can leave this side over here like we ended up with, because it's negative x for x. But now we're going to change the y to a negative y. Well, let's simplify that. What if we divided both sides by a negative to get rid of that negative in front of the y? So that sign would change, that sign would change, that sign would change. Does that match what we started with? Yes, it does. So this one is odd. How about this? And if we want to see if it's even, we'll start with y equals. Again, we're going to put in negative x for x. We're going to put a negative x squared like that. Now, if we simplify that, if we take a negative x and square it, that cancels out the negative, so we get that. Does that match what we started with? Yes, it does. So this one's even. Once you know it's even, you're done. Because it can't be even and odd both. It's either even, or it's odd, or it's neither. That's your three choices. This next one, let's see if it's even. And let's change this to a y equals. Let's put negative x in for x. So it looks like that. Now if we simplified that, negative x cubed stays negative. So it looks like that. Does that match what we started with? No. So it's not even. Let's see if it's odd. Let's leave this right side alone. Leave it like we ended up. Now we want to change that y to a negative y. Now we want to get rid of negative. If I divide both sides by a -1, that's going to change all of the signs. Does that match what we started with? Not quite. This sign is wrong. So this one is neither. Okay. The last thing here is the greatest integer function. I thought I changed this, but I guess I didn't. This should be just a bracket around this. Different books do this differently. We're going to just use a single bracket. If you have a single bracket, this is kind of a tricky function. It seems weird, but this one shows up all of the time in real life, all of the time. This means is that y is the greatest integer less than or equal to whatever x is. Remember, an integer is a positive or negative whole number. So here, if I plugged in numbers, like if you plug in integers like 0, well, the greatest integer less than or equal to 0 is 0. The greatest integer less than or equal to 1 is 1. The greatest integer less than or equal to 2 is 2. Greatest integer less than or equal to 3 is 3. So that part doesn't change. It's the fractions that are different. What if I put in 1.2? What's the greatest integer less than or equal to 1.2? Well, less than 1.2, the next integer is 1. How about 1.5? The greatest integer less than or equal to 1.5 is still 1. How about 1.9? The greatest integer less than or equal to 1.9 is also 1. The y value will always be an integer, or something between 2 and 3, like 2.4. The greatest integer less than or equal to 2.4 is 2. How about 2.7? The greatest integer less than or equal to 2.7 is 2. Let's see what that graph looks like. So we said we had 0, 0, we had 1, 1, we had 2, 2, we had 3, 3. Easy enough. Now in here, when we had 1.2, it was 1. When we had 1.5, it was 1. When we had 1.9, it was 1. Now when we got to 2, it jumped up to 2. So what we have is we're going to have a dot right here at 1, 1. And then we have a horizontal line. And when we get to 2, we're going to put an open circle, because there it jumps up to 2. Same way here between 2 and 3. At 2.4, it was 2. At 2.7, it was 2. So between 2 and 3, we have a dot at 2, 2. We have a horizontal line. When we get to 3, we're going to put an open circle because we jump up to 3, 3. So that's what the graph looks like. Every one, you start on the left, you have a horizontal line, and then it jumps up. That's what a greatest integer function looks like. Well, it looks weird, but it's called, you see it called a stair-step function. Maybe you can see why they would call it that, because it looked like stair steps. A lot of times it's called a postage stamp function, because if you actually graphed what you pay, I know you don't use postage stamps anymore, but if you graphed how you pay for a postage stamp, for a certain weight you pay like 47 cents. Then when you add another, like an ounce, whatever, now you add another penny or whatever to that. So it jumps up like this. Or if you thought of how much you pay for sales tax, let's say your sales tax was 10%. So what happens is you're going to pay a penny for everything up from 0 to 10, you're going to pay a penny. So from 0 to 10, you pay a penny. From 10 to 20, you pay 2 pennies. From 20 to 30, you pay 3 pennies. If you graph that, it looks the same thing. So even though it's a weird looking thing, it actually, a lot of graphs in real life are greatest integer functions or stair-step functions. And that takes care of 1.3.